ME from Anna University, Chennai, and earned his PhD from IIT Patna in 2018. He has also gained international research exposure as a postdoctoral researcher at Shanghai University, Chennai. He is a member of IEEE as well as other international professional bodies and has been recognized among the world's top 2% scientists in the Stanford University listings for 2024 and 2025. His research expertise spans control of time delay systems, load frequency control, cybersecurity in power system, adaptive control, and application of meta-heuristic optimization techniques in control engineering. With his strong academic background, international exposure, and impactful research contributions, we are confident that his session will provide valuable insights into modern model-based control strategies and emerging trends. We warmly welcome Dr. Lloyds Raja to this FDP and look forward to an enlightening session. Sir, the session is to you. Sir, please,
hello,
you
ma'am.
can start.
Thank you for this introduction. Yeah, I
Yes,
hope I
sir.
am still audible.
Yes, sir, you're audible.
So, is my screen visible?
Screen is visible. Yes, sir.
Yes. So, very good afternoon to all of you. So, it is a honor to meet all of you through this virtual platform and share some of the insights into this topic on model-based controller design. So I'm also thankful to Professor Munje for this invitation and an opportunity to interact with all of you. So the topic would be on model-based controller design, and we'll focus on some applications as well as the recent trends in this domain towards the end. So I will keep the initial part of my lecture little lucid so that all of us can understand and correlate. And in between, we'll also switch a little bit to the simulations, some very basic simulation exercises, so that you can connect with these topics in a better manner. So first, we'll start with an overview. What this model-based controller design is all about. And we'll talk about some of the challenges in it. And we'll talk about various models. So I would request the participants to remain muted. So we'll have a time at the end, hopefully, for the interaction as well as Q&A. So it will be convenient for everyone if you can remain muted in between. Okay. So what is a process and what is a process model? So when we try to mathematically represent a system in the form of a transfer function or a state space model, we can call it as a process model or a mathematical model of that particular system. So this model-based controller design techniques are all about how you can design a controller provided the mathematical model or the transfer function of the system is available to you. And then we will see what are the different ways in which the processes commonly encountered in industry are identified. And we will also visit some of the commonly used controller design techniques. And we will see some modifications in the conventional unity feedback control scheme. And in between, we will also see some simulation exercises. And when it comes to this controller design, there is a very important trade-off that needs to be considered. That is the performance and robustness trade-off. So we will spend some amount of time on this trade-off concept as well. And then we will focus on the recent trends and the related literature. So to begin with, let us consider this diagram for a while, which basically talks about the overall steps involved in any model-based controller design process. So the prerequisite for a model-based controller design is that the mathematical model of the system has to be available to us. So even if you are dealing with a very complex system, and if you can obtain some input-output data from that particular plant and use the model identification toolbox in your MATLAB, then you'll be able to come up with a convenient mathematical model of the system. So this requires giving some known input to the system, acquiring or capturing the output over a period of time, and then by using this data to identify the plant structure and coefficients. Then followed by this, we can go for the open loop analysis of this plant model to understand its behavior. And then we can select an appropriate controller configuration by looking at the nature of this plant model. And after that, we can also analyze the behavior of this system, the closed loop system. We can see whether the stability margins are satisfactory or the system is going to be stable. And this can be subjected to simulation validation and followed by prototyping. So while doing the simulation also, because we are discussing primarily on the linear control theory, we have to be sure whether this system will be able to handle non-linearity or not. Because most of the physical systems that you are trying to control involves nonlinear components. So we have to ensure that the controller that you have designed with a linearized model is capable of yielding a stable closed loop performance even in the presence of non-linearity. So this aspect has to be taken care of during the simulation part. And before going to the prototype, we have to be sure about how the system behaves in open loop, closed loop, its various performance indices, whether it is able to handle non-linearity and all. And then we finally go for the prototype. So in a sense, that in today's lecture, we are going through all these stages in some way or the other. So these are some of the challenges in industrial process control. So you may encounter processes that are stable. Fine, it is the easiest among this whole category. And then we have processes which are unstable. So talking about this little mathematically, if you can see your transfer function and you are seeing one or more poles on the right half of the S-plane, you can call this particular system to be unstable. Similarly, if you have one or more poles at the origin, then we can call the system to be integrating. So if you can think of some practical examples for this unstable process, you can have CSTRs, continuously stirred tank reactors, which are of isothermal nature. So they are of unstable type. And then if you have a liquid storage tank and you connect a pump at the outlet of the tank, it can behave as a integrating process. Then boiler steam drums, paper drum dryer can. These are the common examples that are given in the literature as well as the textbooks for the integrating process. Now, controlling these processes are little simple as long as the delay comes into picture. So if there are some delay coming into picture, and these are delay, the inherent delay associated with the process due to the transportation or the recycled loops, or if you are having a loop to analyze the composition of, let us say, the various chemicals in a particular product, then all this can cause dead time into the system. So if you talk in terms of power system, so communication delay is one thing that we cannot neglect in the common modern power system. So that is something very similar to what the dead time in the uh, process control is. So communication time delay in your power system and your dead time here in your chemical process control. So all this, when you are operating that system in closed loop, are going to introduce instability in the response. So this needs to be accounted for while designing the controller. Then inverse response. So some of the processes, when you analyze its behavior in the open loop, you might notice that it will respond in a completely opposite direction than it is supposed to respond momentarily. You can see that the response is in the opposite direction for a while. So this is happening because in the mathematical model of those systems, you will have a right of plane zero. So these type of processes are called non-minimum phase processes or inverse response processes. So when a system has non-minimum phase delay associated with them, it can become even more challenging to control. So summarizing all this, mathematically, I can represent some of the commonly encountered processes in this way. So what you see in the top leftmost corner, it is a simple first order system with a gain K, time constant tau, and a time delay theta. So K is the gain, tau is the time constant, and theta is the delay. So I have in fact given some of the examples for these three category of processes. The top row are mostly the stable processes, and the second row mostly of the integrating processes, and the third row are of the unstable processes. In the right hand side, I have shown how a process in which there is inverse response associated. Let us say a right of plane zero is associated with the transfer function. That example is shown in the rightmost corner. So for a stable system, you can see that all the poles are on the left half of the S-plane. And for integrating, there are one or more poles on the origin. And similarly, for the unstable system, there are one or more poles in the right half of the S-plane. So these are the commonly encountered process models. So these are some of the practical examples which you would even find in the textbooks. So this is a simple liquid level control system which would behave as a stable process. And this is a magnetic levitation system. And you would know that if you want to sustain this metallic ball in its proper position, then you need to properly design a controller. So that is how it is important to stabilize this system. So similarly, if you talk in terms of the inverted pendulum, so if you want to maintain the pendulum arm in the upright position, then you again need to stabilize the system, properly design a controller for this purpose. So this type of laboratory scale setups we have in our institutions as well. So these are common examples for unstable systems. So the inverted pendulum in some literature, people have even identified this as a integrating process. So however, it can also be identified as a unstable process, and the design of the controller can be done accordingly. So similarly, let us consider this block diagram for a while, and we'll see what are the essentials to be taken care of when you design a controller. So first and foremost, the controller should be capable of tracking the given reference value R. So Y I can call the symbol Y I can use to denote the controlled variable, and the symbol capital small d I can use it for the disturbance, and R I can use for the reference or the set point. Now R minus Y will give you the error which the controller is supposed to minimize, and U is the actuation signal that is generated by the controller. So when we design a controller properly, we expect that it should take care of the, first of all, set point tracking. So whatever reference command that you give in R, you expect the Y to follow. And secondly, any sort of disturbance that is entering into the system, D, that has to be rejected by the controller. And then we must also ensure that there is no actuator saturation that is happening. So for this purpose, you should ensure that the output of the controller should be as smooth as possible. So these three primary requirements needs to be taken care of. In addition to that, uh, the controller should not be such that it is amplifying the measurement noise or amplifying the noise that is occurring in the system. So this is also another aspect to be taken care of. Along with this, there is also another important aspect called robustness. So I talked about point tracking, I talked about the disturbance rejection, then I talked about the importance of the control signal to be as smooth as possible. And then I also talked about that the effect of noise should not be amplified. And then the the last thing that I want to put before you is the robustness of your controller. So what do I mean by robustness here? See, when you design the controller, you design the controller based on some mathematical model. And if you have obtained this mathematical model through some sort of identification procedure, of course, this model is going to be 98%, 96%, or let's say some sort of inaccuracy is always associated with this process model. So when you are designing a controller based on such an process model, when you deploy this controller in practice, you need to ensure that the controller is robust. So robustness in the sense that I want to ensure that my controller, which I designed by using some sort of uh, mathematical model of the system. And when this controller is deployed in practice, I want this controller to yield a stable response. So that's what I mean by robustness here. So we need to take care of the disturbance rejection, set point tracking, the effect of noise, as well as the smoothness of the control signal, and finally the robustness of the controller. And of course, we have lot of advanced control schemes these days. We have the sliding mode control, we have model predictive control, and we have the active disturbance rejection control. So fuzzy controllers, and then neuro fuzzy systems. All these controllers we have, but in industry, till date, people widely go for the PID and its variants, particularly the proportional integral controller. So some of the studies and the statistics will show that most of the controllers which are still used in industry, they are of PID type. And majority of them, they use a simple control loop rather than a multi-loop or maybe a cascade loop or something, unless and until it is required, unless and until that sort of complexity is required, people don't go for it. They would try to solve their problem, or they will want their control loops to be taken care of by normal PID as far as possible. So to begin with, we will see some of the commonly used controller design techniques. So these are all model-based controller design techniques. So first of all, the direct synthesis method we will explore. So what is this direct synthesis method? So here, the procedure starts with the mathematical model of the plant, which is given by, I am taking one example, a very simple example, a first order with a time delay, that is k by 1 plus towers into e to the power minus theta s. So a simple first order system with a gain k, time constant tau, and a time delay theta. So I am taking the desired closed loop transfer function. So this is how I want the this y by r, or this closed loop system to behave. So I am assuming this as a designer. I am assuming this desired closed loop transfer function, and then I am going for the actual closed loop transfer function. Actual closed loop transfer function, if you see the diagram in the right hand side, it has a controller C of S. It has a plant transfer function G of S. So in the design point of view, in the control loop, anything other than the controller, we will consider it as a plant model. Let us say this includes the actuator as well. So all those dynamics put together, we will be considering it as GFS. So what Y of s by R of s, we are taking as a actual closed loop transfer function, that is G of s into C of s plus 1 plus G of s into C of s. And then I am comparing the actual as well as the desired closed loop transfer function. I am rearranging to get the controller function. This controller transfer function, what I have obtained is of the proportional integral form. If you come to the side, so I am expressing it in the actual PA form actually. So that is having a proportional gain of tau divided by k into lambda plus theta, and the integral component, it is related to the time constant of the process. This is very simple direct synthesis method. But if you observe the equation for the PA controller very carefully, uh, the proportional gain, it is a function of some sort of parameter called lambda. So this parameter lambda has to be carefully chosen in order to determine the performance and robustness of this controller. So what do I mean by performance? So if I want this controller to ensure fast set point tracking, a fast disturbance rejection, minimal overshoot, so all this I can take care of by proper selection of this lambda. And also, I need to select this lambda very carefully to ensure that the performance robustness trade-off is not compromised. Because what will happen if your planned model, let us say k divided by 1 plus 2s, is very accurate, then your controller would perform better even when you optimize the system. But in practical scenarios, what you end is that you will get a approximation of the actual system dynamics in the form of this transfer function. But when you design the controller based on that approximation, when you deploy it for practice, then you will face robustness issues. So you cannot go for a very small value of lambda, and also you cannot go for a very high value of lambda. If you go for a very small value of lambda, then you may get a very fast response, but this is valid only when the plan model is accurate. But in practice, when you are deploying this controller in practice, you may face the robustness issues. So therefore, you have to select this lambda such that the performance robustness trade-off has been taken care of. So let me proceed further uh, with how I can extend this design for a unstable process. So the first example that I have considered, this is a stable process with a delay. So if you are trying to operate this system in open loop, there is no issue. But if you want to automate such a system, you will be operating it in a closed loop. So that is where this delay will be causing instability in your system. So how can I design a controller, a system which is of this nature with the same procedure? So if you take a plan transfer function k by s e to the power minus theta s, which is of integrating nature, if you proceed with this form, it can it can perform better than the single loop control structure. So in short, I am using two different controllers, C1 and C2. The C2 is primarily meant for stabilizing the system. So stabilizing in the sense that if you see the equation number 3, it has one pole in the right half of the S-plane. But if you can properly design this controller C2, then you can shift the location of the transfer function y divided by r dash. So what is y divided by r dash? If you can apply your block diagram reduction theory, y divided by r dash will be p divided by 1 plus C2 into p. So if you observe the characteristic equation of this, which is actually shown in equation number 5, you look at equation number 5. So in this equation number 5, you have a characteristic equation 1 plus C2 of S into P of S. So if you have the roots of this characteristic equation, 1 plus C2 into P, in the if you can shift the roots of the characteristic equation, which was originally in the right of side of the S plane, if you can shift them to the left hand side, then you can stabilize this system. So this requires careful selection of this KP as well as TD. So how to do that, we'll see in the next slide. So first of all, I am writing this equation number 5. Equation number 5 is nothing but y divided by r dash. So which is P of S by 1 plus C2 into P. And I am substituting the required expressions for P, which is K divided by tau S minus 1 e to the power minus theta S, and C2, which is a proportional derivative controller shown in equation number 2. So here, after substitution, in the denominator, I am going for a Pade approximation of the time delay term. In the denominator of equation number 6, you will encounter a time delay term e to the power minus theta s. You can go for a Pade approximation of that, which will give you 1 minus 0.5 theta s by 1 plus 0.5 theta s. Now, if you can select TD equal to 0.5 times theta, then one of these, the denominator term in the Pade approximation can get cancelled out. So this will further simplify your design. Now you can select the value of Kp in the given range, that is between 1 by k and tau divided by 0.5 times k theta. Then you will be able to stabilize this system. So therefore, the minimum value or the chosen value of Kp to be little make the selection process little more easy instead of going for some sort of optimization within this range. So what we have done is we have gone for the geometric mean of this. So that is to take the geometric mean of 1 by k and tau divided by 0.5 times k theta. You will be able to go for a good selection of this Kp. So if you can use this value of Kp in this plant transfer function, then this will give you a stabilized plant model, that is k dash e to the power minus theta s by tau dash into s plus 1. So this will be possible by proper selection of Kp, which is the geometric mean of Kp min and Kp max. And by selecting tau d is equal to 0.5 times theta. So now that I have stabilized this plant by properly designing C2, so that if I see y divided by r dash as per equation number 5, this will now become a stable system. So I can design the controller C1 for this transfer function y divided by r dash. That's what we are doing here. We are going to design the controller C1 for this transfer function, the stabilized model. So for this, I am going to repeat the same procedure which I discussed in the previous slide. So what I did, I will be assuming a desired closed loop transfer function. Then I will be specifying a actual closed loop transfer function as per the block diagram. Then I will be equating the desired and the actual closed loop transfer function, and I will be rearranging it in the proper PI form. So the same procedure I will be repeating here. So when I do that, I'll get a PI controller which has a proportional gain, that is tau dash divided by k dash into alpha plus theta, and TA is equal to tau dash. So what you will notice once more is that again this PI controller, it becomes a function of a particular tuning parameter or the design parameter, you can call it. So if you can go for a careful selection of this alpha, then you'll be able to achieve a proper performance robustness trade-off, because all other uh, parameters are known to you. You'll be able to get tau dash, k dash, theta, everything from the plan model, from where you actually started this design. So k will be known to you, tau will be known to you, and theta will be known to you. The only unknown thing in this case will be your selection of alpha. So if you can select this alpha in this equation number 10 carefully, you will be able to achieve a proper performance robustness trade-off. So let us start with a simple exercise. I'll stop sharing for a while.
Participants, please wait. The session will be continuing soon.
Yeah, I hope my MATLAB screen is visible right now. And what we are going to do is a very simple exercise based on what we discussed right now. I am taking a heat exchanger model. Basically, this model was identified from one of the laboratories in NIT Rourkela. So this is the integrating process, as you know, 0.002, having time delay of 3 seconds. It's the integrating process. And we will first of all try to stabilize this by using a simple proportional controller. And for designing this proportional controller, we can go for a simple gain, and you can try to adjust the gain, or you can go for a proper method like this, where to select the value of gain. And this is a proper direct synthesis method. And the second thing that we are going to try this exercise is that how we can design a PIPD controller for this particular plant transfer function. So here the K will be 0.002, the time delay theta will be 3, and this is a integrating process. So this falls under the category which you see here, that is K e to the power minus theta s by s. So K will be 0.002 and theta will be 3 seconds. So to make it easy for us, I have written a very simple code actually based on these expressions. All these expressions were in fact presented before you. And this is the plant transfer function. So I am taking a lambda value. Initially, I am taking it as lambda equal to 3. Later on, I will talk about the performance robust trade-off. So when I run this code, these are the settings that I am getting. This is for the simple proportional controller, and then this is for the proportional derivative controller, and this is for the proportional integral controller. And let me open the simulating part where we are basically going to simulate this. So we are going to simulate, first of all, the open loop system. You see, in open loop, how the system behaves. So I have simulated this, the transport delay block for the delay 3 seconds. So I have taken a step change at t equal to 0 second. And you can see that no controller, no closed loop. And you are getting some sort of unbounded response. And now I'm not going to still use the controller. I'm just connecting this process in closed loop. No controller as of now. So I have connected this in the closed loop. Now you can see that it is still not stabilized. It is still giving unstable response. Now I'll go for the proportional controller, and I have calculated the proportional controller gain like this as 83.33. You can also, of course, vary this and see the effect on the performance. So this proportional gain I have given here in the closed loop system. So this is your planned transfer function, and I have also simulated some disturbance to show its effect. So this is the response that you are getting for the closed loop system. So here still the drawback that you are noticing that I am using a single controller, a proportional controller. I am able to get a stable response. But the moment I apply the disturbance, in fact, I have applied the disturbance around 50 seconds. You might notice that at 50 seconds, I have applied the disturbance. And the delay associated is around 3 seconds. That is almost after 53 seconds, you can see the effect of the disturbance here in the response. And the response never settles back to the desired value, that is 1, because there is a steady state error that is happening. And you require some more alterations in the control structure. So that's where the PIPD control structure comes into picture. So here started with the proportional, and now we are going to use these settings, which is the PIPD control structure. So we actually discussed about this in the slides. So I'm going to formulate this type of control structure. There will be a PA controller in the feed forward path, and there will be a PD controller in the feedback path. So this is what I have simulated. You can see at the bottom. So this is your planned transfer function, 0.02s. And I have considered the same disturbance at 50 seconds with a final value of 5. And whatever the proportional gain, whatever the integral time constant that I have got through my calculations, and this is my proportional derivative controller. When you implement the proportional derivative controller, you have to always do it in series with the filter. One thing is that it will make the Kp into 1 plus Td into S as a proper transfer function. Secondly, it will also help you to own the measurement noise. Okay, so the derivative term always comes in series with the filter. So here you have obtained your derivative in proportional gain as well as the derivative value, that is TD also. So after this, I'm running the sim. Now, exactly at 53 seconds, the effect of the disturbance is seen. But over a period of time, this disturbance is rejected and the response returns back to the desired value, that is 1. Now, if you see a comparison of what you have obtained in the simple proportional controller and the PAPD control structure. So what you see in the yellow plot, this is a simple proportional controller, and the pink plot, it is nothing but your PAPD control structure. So in the first case, you got a steady state error, but by properly designing a PI/PD control structure, you are able to achieve a disturbance rejection as well. So this brings me to the second method of model-based controller design, which is internal model control structure. So again, we'll go through this internal model control structure theory first of all, and then we'll see some very basic simulations. So what is this internal model control structure? You have a process, and then you have the mathematical model of the process, which is now part of the control loop. And you are using this GM in order to design the controller GC. What are the steps involved? You have to first decompose the process model into invertible as well as the non-invertible components. The invertible component is denoted by the sign minus and the non-inverting component by plus sign. So what is the inverting component consist of? It consists of the delay-free part of the plant transfer function GM. That is, if you see this k divided by tau s plus 1, that is your delay-free part. So this GM minus basically consists of the delay-free part of the GM. And what is the non-invertible component, which is the GM plus? The plus component, it consists of time delays, or if you have any right of plane 0 in the plan model, that will also be part of the non-invertible component. So IMC theory says that your controller can be obtained by finding the inverse of the invertible component multiplied by a filter of suitable order. And this filter, order of this filter, in general, I should have written it as tau s plus 1 divided by k into lambda s plus 1 whole power n. So this filter's order will be selected based on the so the order of this filter will be decided based on the order of the plant transfer function, so that you get a proper transfer function, that is GC star of S. Now in the left hand side, I have written an equation GC equal to GC star divided by 1 minus GC star into GM. So if you want to reduce this internal model control structure into a classical feedback control structure, then you have to apply this transformation. So that will help you to express the IMC filter or the controller GC star in the form of a proper PID or its variants, so that you can convert this internal model control structure into a classical feedback control structure. The key is the transformation that you see here in the bottom left, that is GC star divided by 1 minus GC star into GM. So this is about the internal model control. And let us take up a very simple example in this case. So this example is e to the power minus s divided by s plus 1. So here the gain k is equal to 1, time delay is 1 second, and time constant is also 1. So in this exercise, we are going to see how the response of the system will vary depending on the selection of this lambda. So here, again, if you see this equation at the bottom, it has a tuning parameter lambda. And this tuning parameter lambda will again be the key for determining the performance and robustness of this design. So therefore, in this exercise, we will see by selecting different values of lambda, how the response in the same time, we also consider and we will see how the lambda remains the key in achieving the performance robustness data. We'll go back simulation using the previous simulation. So if you can recollect, this is the exercise that we have taken up. So I have to design a IMC based control structure for this plan model, that is e to the power minus s divided by s plus 1. Coming to the simulation. So here I have first simulated the plan transfer function in the open loop. I have given a reference. You can see the reference, that is a step change at equal to 0. Final value is 1. So that I expect the output to be 1. Running the simulation, you can see that operating the open loop, and you are having a disturbance here. This disturbance is not rejected. I am giving a disturbance at 15 seconds, and the disturbance is not. So go for the so in the closed loop, no controller involved, just operating the system, the very same plan transfer function in the closed loop. So in this case, here you are note that the rest become more oscillatory, and the main problem is that it has still not reached the desired value. It has not reached the desired value. You can see initially it is settling somewhere here around 0.5, and then after you gave disturbance, it is again becoming oscillatory, and maybe if you had gone for a higher value of disturbance, it may not settle at 1. Now in the third case, what I have done, I have applied this internal model control theory. So this is the typical internal model control structure that I have shown to you. So here I have taken the plan transfer function 1 divided by s plus 1, and the delay is 1. And what block diagram am I trying to simulate? I am trying to simulate the second block diagram, internal model control structure. So for GM, I have exactly used this same plan transfer function, that is e to the power minus s by s plus 1. In the case of the process, which is GP, what I have done is I have slightly perturbed this plan transfer function. I have introduced some 20% variation here, so that this 1 becomes 1.2 and this theta becomes 1.2 as well. So if you see this, I have introduced some 10%, 20% change transfer function here in order to illustrate the robustness of this design and the role of selection of lambda. So I have 20%, and the delay also 20% perturbation I have considered. Originally it was 1, I have made it 1.2, and the planned model I am keeping the same, because based on this planned model only we have designed this controller, and this particular study is being done in order to show the effect of lambda and its role in robustness. Now, when you run the simulation, you can see that the plan is stabilized also, and it is reaching the desired value, that is 1. And this is the effect of the disturbance. And after disturbance, due to the action of the controller, it is getting settled as well, again at 1. Now, in the second case, what I have done, previously I have taken the value of lambda to be 2. Okay, lambda I have taken as 2 here. And the second case, I have taken lambda equal to, let us say 0.1, very small value I have taken. Okay. And third case, I have taken lambda equal to 1. So this basically get cancelled out. So you have taken lambda equal to 2, a high value. Then lambda equal to 1 I have taken, and lambda equal to 0.1 I have taken. And in all three cases, I have taken the internal model to be 1 by s plus 1 e to the power minus theta s. And in the case of the plant, I have considered 20% perturbation. So this basically simulates the variation between your plant as well as the actual system dynamics. Now we'll be able to see the effect of this three. Okay. And you will see that in one case, you are getting a completely oscillatory response. So you can see you are getting a completely oscillatory response in the that is corresponding to lambda equal to 0.1. So this is the response corresponding to lambda equal to 0.1. The response is completely here in the last day. So I selected a very small value of lambda, then I resulted in this unstable response. So when you go for a proper selection of this lambda, you'll be able to achieve a good performance as well as a satisfactory robustness. And this brings me to the another model-based controller design method. In fact, we are going to talk about a Smith predictor. So why are this Smith predictor is required, and what is the benefit of this Smith predictor? So other name of this Smith predictor, I can call it as a delay compensator. So how it is going to compensate the delay in the system? Let us see with the little bit of mathematics. So So here you have a controller GC, which you have to design based on the process model. So before going into the design part, let us write the actual closed loop transfer function, in this case, y divided by r. So when you write the transfer function y by r for this block diagram, you will be getting gc into g e to the power minus theta s, which is your process. And then you have a process model, which basically has a delay free part gm and a delay that is e to the power minus theta ms. So this theta m is basically the model of this delay in the actual system, and gm is the delay free part of the process model. When you find y by r, this is the expression that you get, that is gc into g e to the power minus theta s by 1 plus gc into gm 1 minus e to the power minus theta m into s into gc into g e to the power minus theta s. Now, if you can go for an assumption where the plant and the model are perfectly matching, which is the g e to the power minus theta s term and the gm into e to the power minus theta m s are perfectly matching, then two of the terms in the denominator will get cancelled out, which will result in a much simpler equation, that is y by r equal to gc into g by 1 plus gc into g into e to the power theta s. So what is the benefit of this Smith predictor? That you can understand by looking at the last expression. You see the characteristic equation of the last expression, that is the denominator. See the denominator doesn't have a delay time, which means you can now design this controller GC without considering the delay. So which will basically simplify the whole process. So we'll take again a very simple example on to see the effect of this Smith predictor. So I have taken a Planck transfer function like this, k e to the power minus theta s by tau s plus 1. And when I find the y by r, let us say using this last expression, I get gc into g divided by 1 plus gc into g multiplied by e to the power minus theta s. Again, I am going for a desired transfer function as I have been doing in the previous cases as well. And I am finding the actual closed loop transfer function. I am finding the desired as well as the actual closed loop transfer function. Then after that, I am replacing the actual one with the desired one. I'm replacing the actual closed loop transfer function with the desired closed loop transfer function, and I am going for a simple rearranging to get a PI controller. So I have arrived at a PI controller. Again, if you see the proportional as well as the integral gain, both of them have a lambda term here. Again, the lambda selection comes into picture, and whatever trade-off that I just discussed and demonstrated through the simulation is also valid here. Just a minute. So just like the case of direct synthesis as well as internal model control, here also if you are going for a this direct synthesis approach for this Smith predictor, the lambda selection becomes a key. So we'll see how this can be affecting the dynamic performance, because I am going to take a planned model with a dominant delay. I'm going to take a higher value of delay, 10-second I'm taking, because you'll be able to clearly see the advantages of the Smith predictor, because this whole Smith predictor structure you will be using whenever you are having a system with a large time delay. Because when you have a system with a large time delay and you don't have a Smith predictor, you are going with the normal control loop, what you will notice is that there will be sluggishness in your servo response, which is the set point tracking. So how the Smith predictor is going to overcome this? I am going to perform two design. One is with Smith predictor I have done, and then I have done another simple design without a Smith predictor. And then we'll see a small comparison of this. So this is the response which actually got without a Smith predictor. This is the response with the Smith predictor actually. So so this design becomes very simple because the benefit that I am getting by using this Smith predictor arrangement is that this equation for y by r there is no time delay term in the characteristic equation, which allows me to design this controller without considering the delay. So which basically overcomes the sluggishness associated with the set point tracking, which was originally not, which was the case without the Smith predictor. Now, this brings me to another alternative of this unity feedback control scheme called the cascade control structure. So I have shown a conventional unity feedback control structure as well as a cascade control structure. What is the difference between these two? You will notice that there is a additional controller and an additional sensor that is involved. So this GP2 and GP1 put together, this will form a single system only. It is actually a single system which is having an intermediate output Y2. So when you have a intermediate output Y2 and you can implement a cascade control structure like this. So typical example I can give in your DC-DC boost converter. So if you see a boost converter, which is meant for boosting your input voltage, and there will be a two modes in which you can operate the boost converter. You can either operate it in a voltage control mode if you are going for a closed loop system, or you can go for a current control mode. So in voltage control mode, you are going to just control the output voltage. So in the case of current control mode, basically it becomes actually a cascade control implementation over there, where you are trying to control the output voltage of the boost converter by controlling your current, which is the inductor current which you are controlling. So that inductor current becomes your Y2 and your output voltage becomes your Y1. And this R1 becomes your voltage reference that you are giving. And this U2 becomes just like your duty ratio in that case. So U2 is your manipulated variable or the output of the controller. And Y1 is your output, which is the output voltage in the case of a boost converter. And in the case of R1, which is your voltage reference that you are giving. So why do I call it as a cascade? You can see the arrangement of the controllers C1 and C2, GC1 and GC2. The output of the first controller, it will serve as a reference for the second controller. And what benefit I am getting out of this cascade control structure is that if you have any disturbances, let's say D1 and D2, without this cascade control structure, you have to wait for this disturbance effect to be felt in Y1, and then the corrective action will take place. But with the help of a cascade control structure, you have an intermediate loop. And if you can design this controller GC2 such that it can respond faster, then you can take care of this disturbance here itself, and you don't have to wait for this disturbance to affect Y1 and then the corrective action to take place. So you are getting a better disturbance rejection in the case of a cascade control structure. And what you need to add, you need to add an additional controller and a sensor, intermediate sensor and a controller. So this is a practical example which you will find in the textbook also. So what you are trying to control is that the hot oil temperature you are controlling. And in this natural draft furnace, the cold oil is entering and the hot oil is coming out. And let us say if the disturbance is happening in the cold oil flow rate, if the disturbance is happening in the cold oil flow rate, then what you have in the left hand side is the unity feedback control structure with one controller and one sensor. And this is more than sufficient to take care of the disturbance. On the other hand, if you are if there occurs a disturbance in the fuel gas pressure, if the disturbance is happening in the fuel gas pressure, then you have to wait for that effect to be felt in the hot oil temperature, and then the corrective action will take place. If you are still sticking to a unity feedback structure, this is the case. If there is a disturbance in the fuel gas pressure, then you have to wait for that effect to appear in the hot oil temperature, and then the corrective action will take place. And this is the case if you are going for a unity feedback structure. However, if you are going for a cascade control structure, then this corrective action will be taking place here itself, because you are having a fuel gas, yeah, if you are having a pressure sensor here, and then you are having a controller here. So if there is any disturbance in the fuel gas pressure, that is taken care of here itself. So you don't have to wait for this effect to be felt in the hot oil temperature. Similar example you can see in the case of a CSTR as well. So here you can see heat emitting reaction. Let us say exothermic reaction is taking place inside this reactor. And unless you control the temperature of this reactor, then it can become disastrous. So therefore, a cooling jacket is used to pump the cold oil around this reactor in order to keep the temperature into control. So the intermediate output in this case, if I can compare this setup with this block diagram, the jacket temperature becomes your Y2 and the reactor temperature becomes your Y1. And the reference, which is the desired temperature of the reactor, becomes your R1. So any disturbances that is happening in the system are D1 and D2. So this is two examples which you generally see in the textbooks, and this is a common block diagram of a cascade control structure. So at this point, I would like to talk about the performance robustness trade-off, which I have been illustrating through some simulation examples as well. If you are going for a smaller value of time constant, you will get better performance, a better servo performance, set point tracking. You will get a better disturbance rejection performance, but it will affect the robustness. However, if you are increasing the closed loop time constant, it will improve the robustness, but at the same time, it will compromise the performance. So this is a becomes a trade-off between the performance and robustness when it comes to the selection of the tuning parameter. And these are some commonly used performance indices: integral absolute error, integral of time weighted absolute error, integral square error, total variation of your control signal. And talking about the performance, we expect that the error matrices as well as the total variation of the control signal, which actually denotes the smoothness of the control signal. So when you see, if you look at this equation very carefully, it basically it takes two different samples of control signal and basically finds the difference, and it keeps on doing it for all values of u and then adds them together. So you get the total variation, which is a measure of smoothness of the control signal. So all these measures can be used to compare the performance of your controller. And also, if you are going for some optimization based approach to design the controller, this can serve as the objective functions as well to design the controller. So these are some performance measures, and all this are function of the error. So how to find the error? You can see this block diagram. So R minus Y, that gives you the error, and all these performance indices are basically function of that particular error. So then, followed by this, I am going to illustrate a very simple procedure, how to design a cascade control structure using a internal model control structure. So basically, you have to go for this IMC theory. We have seen some example also for this IMC theory. So the same procedure you have to repeat two times for the cascade control structure. First, you will start with the inner loop. You will complete the whole procedure, and then you will somehow approximate the inner loop into a simplified form, and then you will go for the outer loop design. So basically, in short, I can say that this internal model control procedure you are repeating two times in order to perform this particular design. So I'll take up another design procedure, which is for cascade control structure. using direct synthesis method, I have taken the inner loop plant model as K2 by 1 plus tau 2 into S e to the power minus theta 2S. And in the outer loop, I can go for three different cases of stable as well as the integrating process. And we can see how a direct synthesis method can be used for this design. So when I go through this design procedure, you can basically get an idea how to use the direct synthesis method for designing a cascade control and how to use a internal model control method for a cascade control structure. So for both the procedure is same. We'll start with the inner loop and the inner loop plant transfer function. And I have gone for the desired closed loop transfer function. I have written the actual closed loop transfer function. I have compared the both, and then I have approximated the delay with the Taylor series symbol, Taylor series approximation, and then I have arranged it in a PI form to get the equation that you see here. This equation already we have derived for a single loop. And now what is the difference when we go for the outer loop? I'm going to approximate the entire inner loop with this desired closed loop transfer function, that is e to the power minus theta 2s by lambda 2s plus 1. So because when I started my design in the inner loop, so this was the assumption based on which I proceeded with the design. So when I do the outer loop design to simplify my procedure, what I have done, I have replaced the entire inner loop with this y2 by r2 d. And this is how I have got this reduced block diagram. And now I can design this controller GC1 by using the other two blocks in the control loop. So the other two blocks consist of the inner loop dynamics, the desired value, and the primary loop plant transfer function GP1. This GP1 can be any of these cases. In this particular case, I have taken this stable first order plus time delay, integral plus time delay, and second order integral plus time delay. It can be any of these cases, or maybe something other than this as well. And this is the procedure. I am basically extending the same direct synthesis procedure. I have taken a desired closed loop transfer function. This time I have taken a higher order because you can notice that we have now come the outer loop. We have to consider the inner loop dynamics also and the plant transfer function of the outer loop also. So I have gone for a slightly higher value of the desired closed loop transfer function, higher order I have taken. And I have applied the direct synthesis procedure. The actual closed loop transfer function is given in equation number 13. And then I have compared the desired closed loop transfer function in 12 with 13. I have rearranged it to get the controller transfer function GC1. And here also, as you are anticipating that in the outer loop, the delay will be little more significant because you are basically adding up the delay of the inner loop plant model as well as the outer loop plant model. So I am going for a better approximation of this delay here, equation number 15. So as I have gone for a little more complex approximation of this delay, you will see that my controller equation is also a little more complex than the previous case. I have obtained a PID controller in series with the lead lag filter here. Okay, so this is again another approach, but the procedure is same. It is the direct synthesis procedure, which I dealt with in detail in the uh, previous slides. So you'll see some examples of this cascade control structure. Okay, I hope my MATLAB screen is visible. So what I have simulated here is the slide I am showing once again. So what I have simulated is this particular block diagram in the or as well. So this is the block diagram which I have simulated. So and the AC as well as the TI values, which represents the inner loop controller, is designed by this procedure as per equation number 11. And then equation number 19 will give you the outer loop controller GC1. Taking you back to the simulation. This is the response. So intentionally, I have simulated three different disturbances. You can see one is having much more effect and the other two are having less effect. And these disturbances are simulated at, let's say, 200 seconds and 400 seconds and one at 600 seconds. You will notice that these two disturbances are basically occurring in the inner loop. And if I had gone for a single controller, and you would not experience the same amount of disturbance rejection performance that you see here, because this intermediate sensor that you have here and the intermediate controller, that is the PA controller that you have designed here, it will take care of these two disturbances in a better manner than a unity feedback scheme. Okay. So this is about the cascade control structure. In the remaining time, I would like to take you through some of the recent trends as well as some interesting application that you can explore. So this is the example. If you are an electrical engineer, you can explore some of these topics for designing your model-based controllers for some interesting applications. For example, if you see a DC-DC boost converter, a simple DC-DC boost converter, if you obtain the transfer function of this, what you will experience is it is a non-minimum phase system. You can see that the numerator you are having a right of 0. And if you substitute this parameter values, the transfer function that you will be getting is what you see here. So it is a non-minimum phase system that you are coming up with. How we will design a controller? Of course, we have discussed the direct synthesis approach, the internal model control approach, and all these are applicable for this Pleasant model. Once you obtain the transfer function, you can apply any of these procedure and you can go for a careful selection of this lambda in order to properly tune the controller so that you don't have to go for hit and trail. Today, even if you want to go for a proper selection of this lambda, you can go for minimization of any of this performance index because it is altogether one parameter and you don't even require a complex optimization procedure. If you go for a simple minimization of integral of square error or integral of time weighted absolute error, you'll be able to get a proper selection of this lambda. So all these model based controller design techniques becomes essential. And for your suggested reading, I will also prescribe this particular literature where you will find that a PID controller has been designed for a boost converter as well as a quadratic boost converter. and both are of different order. In fact, the quadratic boost converter is of higher order, and this is of just the normal boost converter, it is of second order. So irrespective of the order and complexity of your boost converter, this particular literature, it offers a unified approach which you can basically use
Excuse
for
me, sir.
boost converters of, yeah.
Sir, may I interrupt? Sir, your
Yeah.
PPTs are not visible. Can you share it?
Okay, sorry. I think my screen is not shared. Huh?
Yeah, screen sharing is not.
Okay, so this was the slide that I was discussing. Okay, now is it visible?
Yes, sir. Yes.
Yeah. So I
Yes.
was talking about how we can extend this model-based controller techniques for some interesting applications. So one thing that I was talking is about the boost converter. So if you observe the dynamics of the boost converter and you obtain its transfer function, you are basically getting a second order transfer function with a right of plane 0 in the numerator. Okay. So this is an example of a non-minimum phase system. You can see there is a right of plane 0, and you can extend any of these model-based controller techniques, the simple ones which I just discussed, to this particular circuit. And even you can extend it for other boost converter which are of higher order. So you read this literature which is cited at the bottom. So case studies are shown on two different boost converters. One is a normal boost converter, a simple one, and a quadratic boost converter, which is of higher order. So irrespective of the order and complexity of the boost converter, so this literature presents a unified PID controller design approach, which you can apply for boost converters of different order. So this is a variant of direct synthesis approach. You can go through this if you are interested. And then coming back to power systems. So in power system, as I mentioned, modern day power systems, you can treat them as cyber physical systems because of the physical as well as the cyber layer involved and the occurrence of communication latency. If you read the POSOCO report, it says that when the frequency measurements are transmitted to the control center, so there is up to 2 to 4 seconds of delay involved. So this is again a communication delay which can be treated as e to the power minus theta s. And if you obtain the transfer function of this primary loop here, which involves the governor, turbine, as well as the generator dynamics, as well as the droop 1 by R. So you get a third order transfer function as And these are some of the literatures which I would suggest, which deals with the design of robust controllers for power systems, especially in modern day power systems. Cyber attack is a very important issue. So we never know what is the type of cyber attack that is happening. So what we can do and what it is more practically feasible is that you can improve the robustness of your controller. In fact, when you design the controller, though you are not designing it for any specific type of attack, after you design the controller, you can simulate various type of attacks which are of false data injection or denial of service category, and you can check the robustness of your controller in all these cases. So these are some of the literatures that I would like to suggest, especially the first literature, it actually uses a Smith predictor approach, which we just discussed. And the second literature, which I am suggesting, it uses a triparametric fractional controller. You see, nowadays, lot of focus is being done on fractional order controllers because it is expected to have better robustness and performance than integer order controller. But at the same time, if you see the fractional order controllers that are coming up, they add to the number of parameters, and that will add to the complexity of your design procedure. So what we have done in this work is we have gone for a fractional order controller, which is having the same number of parameters like a PID controller, and we have seen how effectively it can deal with the communication delay and cyber threats in the modern power systems. So some more related works I have suggested here. So if you are interested in biomedical applications also, you can try this approach. So recently, one of the PhD students in our group, he developed a biomedical suction device. He's also from Maharashtra only. So he developed a biomedical suction device for uh, and he has implemented a pressure control loop in that. So this suction device is meant for taking out the meconium fluid from the newborn child's lungs. Otherwise, if you don't take out this meconium fluid, then it will result in a meconium stained amniotic fluid inside the baby's lungs, and it can result in the meconium aspiration syndrome, which is a commonly occurring disease in the newborn. But if you look at the present medical devices available, they mostly go for the manual suction, and we are supposed to maintain a very safe suction pressure. And in fact, this particular prototype has underwent 2 or 3 changes as well in future. We have also implemented cascade control structure in this prototype, and we have also developed a variant in which there is a safety valve involved in case the suction catheter goes and touches any part of the baby's body and the pressure gets abnormally builds up in the suction flask, and how to release that pressure using a safety valve. So 3 different variants of this design we have done, and one using a single controller, and other using a 2 sensor and 2 controllers, and third one using a controller and a safety valve. So the details you can get it in this literature. I'll be sharing the slides with Professor Munje after this, and I hope you'll be able to circulate with you. So with this, I would like to acknowledge all my students as well, because some of the works that I have presented before you, basically it is their research, for which I would acknowledge all of them. And now let us have some discussion.
Yeah, currently it's scared.
Uh, I would like to take up some questions, if there are any.
Participants, you can unmute yourself if you have any questions on this session.
Yes, madam.
If you have difficulty in speaking out, you can put the questions in the chat as well. I'm opening the chat. In case you have any questions, you can put them in the chat as well. So if you need all these slides and the basic simulations can be shared with you. So I hope it will be useful for you. And if there are anything more that you would like to discuss with me, you can contact me in these details. So details are also given in the first slide. And I hope some interesting and practically relevant applications you can explore with this simple techniques.
Any question by participants? It was very wonderful session, and a very basic level. You started with a very basic kind of introduction, which we all know, but finally you took us to the last stage, which is very important. So thank you very much for giving this much kind of introduction and depth for the topic. Any question by participants? Okay, if there are no questions, Merin?
Thank you so much, sir. I sincerely thank Dr. G. Lloyds Raja for delivering an insightful session. The discussion on system modeling techniques, controller design methodologies, and the implementation examples on the boost converter power system, pressure control in meconium actuator, using this model-based control was especially insightful for us. It was a privilege to participate and gain valuable knowledge from this enriching session. We also thank the attendees for their active participation, and we look forward the participation in the upcoming sessions too. Thank you once again. So with this, our first session is over. So we can move on to the second session. Sir, can we start with the second session, sir?
Yeah, thank you, Dr. Raja. Thank you for
Thank you so
joining.
much.
Thank you very much. And I once again would like to thank you, and I would like to inform to all the participants, like he is one of the pillars of this international faculty development program, because he has helped me in getting the speakers for this FDP. Not only for this FDP, but for earlier FDP also, he has given supported me in getting the speakers. So thank you very much. Okay, Merin, we can go ahead.
Thank you, sir. Thank you, sir.
Yeah.
Thank you.
Thank you. Thank you. Bye.
The next session is by Dr. Tarakanath Kobaku. I think he is
He
present
is
in the
there.
session.
He is there.
Okay, let me introduce
Dr. Tarakanath, you are there? Can you
Yes, sir. Yes,
Yeah.
sir. I already joined.
Yeah. So we can start.
Yes, it's our privilege to introduce the second speaker of this faculty development program, Dr. Tarakanath Kobaku. He will be delivering a lecture on robust control design of non-minimum phase systems under input saturation, case studies in power electronic converter. Dr. Kobaku is currently an assistant professor in the Department of Electrical and Electronics Engineering at Pilani, KK Birla Goa campus. He received his BTech degree from JNTU Hyderabad, completed his ME in Control Systems from Birla Institute of Technology, Mesra, and earned his PhD in Electrical Engineering from IIT Bombay. His research interests lie in robust control and its applications in power electronics converters, along with mechatronics, energy storage systems, and fuel cell systems. He has received research funding from leading national agencies, including DST, ISRO, and SERB, highlighting the relevance and impact of his work. Dr. Kobaku is a recipient of the prestigious DST Inspire Faculty Award 2018 and was rated very good in the DST Inspire Faculty Scheme Performance Evaluation in 2023. In addition, he has received the Excellence in Teaching Award twice at IIT Goa, a travel grant from the European Embedded Control Institute, and was MHRD Fellow during both his Master's and PhD studies. With his strong academic foundation, funded research experience, and deep expertise in robust control of power electronic system, we are confident that his talk will offer valuable theoretical insights and practical case studies to all the participants. We warmly welcome Dr. Tarak Kobaku to this FDP and look forward to an engaging and insightful session. Over to you, sir.
Yeah, thank you. Thank you for the nice introduction. So I'm sharing my slides. Please let me know if they're visible. Please let me know whether the slides are visible.
Yes, sir. Yes, sir. Slides are visible. Please proceed.
Yeah. So the title, of topic is robust control design of non-minimum phase systems under input saturation. So I have taken a few case studies in power electronic converters. So by the end of this talk, we should be able to understand why the design of controller is very challenging, particularly for non-minimum phase systems, and what is meant by an input saturation, and how to overcome the input saturation using the robust control design. So the bits so I think these are not required. And just only one slide I would like to discuss is I am currently having 3 PhD students, and in particularly I'm looking for this BITS RMIT Australia for a PhD student. If anybody is interested, RMIT Australia's the QS ranking is 116, so it is a decent institute. I'm like across the globe. So if you have any interest, I mean, in these areas of controls, power electronic converters, fuel cells, energy storage systems, you can approach me. So we have a very strong Goa campus. Yeah. So these are the first one is my work, which was published on attribute transactions and power electronics, where we discussed on DC-DC converter, which is a boost converter. And the second paper is a conference, which is extension to the first paper. So how to overcome this reset wind-up saturation issue using the anti-reset wind-up compensation along with the FPGA implementation. So these are the first, these are the first 2 papers. These 2 papers I will be discussing in this presentation. If time permits, I will go into the third work. So this is the outline of the presentation. So I will basically start with the non-minimum phase systems and what are the challenges from control viewpoint when we want to design a robust controller for a non-minimum phase system, and what do you mean by a model-based control, how to implement a model-based control, and what are its limitations, and how to overcome these limitations using the 1 degrees of freedom internal model control, and again what are its limitations to overcome these limitations of 1D OF. So hereafter I will be using IMC as a short form for the internal model control. So how to overcome the limitations of 1D OF IMC using the 2D OF IMC. Again, they have its limitations, these unconstrained limitations of 2D OF IMC. So how to overcome these unconstrained limitations using the anti-reset wind-up compensator under IMC. And I will be looking again. I will be discussing about the simulations as well as the experiments, and this direction-synthesis approach of designing PID and modified direction-synthesis approach PID. If time permits, I will look into these algorithms. So where are these non-minimum phase systems actually useful or applicable in practical day-to-day life or practical applications? If you see, there are microgrids. Many of us have come across this word. If you see on the left side, we have a single bus DC microgrid, which is where the energy storage systems are directly connected, like battery is directly connected to the DC bus. But if you see on the right side, if the energy storage systems are again connected through power electronic converters. So overall, if you see this DC microgrid, to work efficiently, these power electronic converters are the basic building blocks, and their major use of power electronic DC converters is to supply or to provide constant DC output voltage across the DC microgrid. So this is the DC bus. If you see here, this is a DC bus, and across this bus we are expected to have a constant output voltage irrespective of the disturbances, external disturbances, where there can be a fluctuation in the PV voltage or this DC loads or the AC loads. But however, irrespective of these fluctuations or these disturbances, we're expected to have a constant output voltage. So this is a control a problem. But however, if you see here, there are these kind of boost step DC converters, which are basically step-up converters. So for example, if the input voltage to the boost converter is 5 volts, it basically steps up to a voltage greater than 5 volts. So depending upon the control input. However, this boost step DC converters poses a certain challenge called the non-minimum phase dynamics. Even though they're useful, but it comes with a certain difficulties in control design. However, they have a lot of applications. This is one application, DC microgrid. If you see in energy storage system or by using the fuel cell integration, even the fuel cell provides a DC output voltage and DC current. However, it requires again a boost step DC converter to step up its voltage. Even for solar PV application, a boost step DC converter is required. And again, if you see with energy storage system, there is a bidirectional DC converter. One direction it operates as a boost operation, where the battery or the ultra capacitor is in the discharging condition. However, if you see here, there is a DC bus connected across, be it solar panel PV, where it is a source, or a fuel cell is a source, or energy storage system is a source. This DC bus voltage is expected to have a constant output voltage irrespective of these variations in fuel cell or solar PV or in energy storage system. So that's why we require these advanced control schemes. So in particularly, I have employed internal model control scheme. So I will be explaining why I choose internal model control scheme over, there are many robust controllers like sliding mode control, which is very popular, but they have its own limitations. So even in electric vehicles, if you see, apart from DC microgrids, converters, particularly these booster DC converters, are explicitly used, as an interfacing converter with the energy storage systems. And even if you see, even if you see in the portable devices, even in the portable devices, this boosted DC converters or even buck-type DC converters are explicitly used, and we will be looking in particularly this power converter, which is boost converter, and what are its issues. So for more details of this portable device, maybe you can look at this particular transaction on power electronics. So we'll start with let's understand that so these are difficult to control. But why they are difficult to control and what are its fundamental limitations? If you see, there are three fundamental limitations when we encounter a non-minimum phase plant. So the three fundamental limitations are: we will not be able to achieve desired level of disturbance rejection, we will not be able to achieve desired level of tracking reference signal, we will not be able to achieve desired level of robustness to plant parameter variations. You design any controller, it is not possible to overcome these three fundamental limitations. But how can we can use intermodal control scheme, and then we can go close to the non-minimum phase dynamics. So that's the best possible we can achieve. So we'll see how to achieve close to its limitations. And there are two categories of non-minimum phase plants. So the category 1 is a plant with a time delay, and the category 2 is a plant with a 0 on the right hand side of the S plane. So these are the two fundamental categories of non-minimum phase plants. If you see the plants with a time delay, where P1 of S is a minimum phase plant, and you're multiplying with a time delay operator e power minus st. So when we have such a plant, and if you give the input, you see this is the input u of t. If you give the input at t equal to 0 seconds, you don't see the output till the time of capital T units. Only after the elapse of this T units, we'll start looking at the output. So this is the peculiar behavior, so which we classify it as a non-minimum phase behavior, and e power minus st is the non-minimum phase component. The other classification is if you have a 0 in particularly on the right hand side of the S plane. So if you see here a power minus s, so a minus s, if you see there is a 0 on the right hand side of the S plane, if you have such a 0, what happens is that even though I am applying the input at t equal to 0 units, you see here, the plant does not respond in the same direction. See, even though I'm applying the input in this direction, in the positive direction, the plant responds initially in the negative direction and then comes back to the direction of the input. So this is another typical behavior of non-minimum phase plant. So both this time delay and this non-minimum phase, this RHP0, they pose fundamental limitations in the control design. So I will take an example of time delay, and we will see what are its fundamental limitations, and the same, the qualitatively it is applicable for the RHP0 as well. So we'll just look at the frequency response of a time delay. So if you look at the frequency response of the time delay, so how we calculate the frequency response is by substituting s is equal to j omega. So if you look at this time delay operator e power minus st, and we let us look at the frequency response. So that is the magnitude and the frequency response. If you look at the magnitude response, it does not change. If you see e power minus j omega t, its magnitude is equal to 1. So this term e power minus j omega t does not change the magnitude characteristics of the plant P1 of S. So it is the magnitude response of P of S and P1 of S are same irrespective of the frequency. Now let us look at the phase response. If you look at the phase response, you see here it is minus omega t. So this term e power minus omega t contributes a phase lag which is directly proportional to omega frequency. You see here. Now let us look at the the frequency plots. So the magnitude wise there is no issue, but if you see the frequency wise, there is a lag coming in the form of minus omega t. It is coming from the frequency, from the phase response. So you see here the magnitude response, there is no issue, but you see this is the major issue. The frequency, the phase lag is getting increased as you increase the frequency. You see here, this is the basic, the problem. So as a result, what happens is the amount of phase margin that is available will be significantly low or negative. So that's the issue that this minus omega t brings to the overall plant P of S. Now let's try to understand into more details. So to understand in a better way, I have constructed some examples. So let us take a simple first order plant 100 by S plus 10, where we can see the magnitude and the phase response. Those first order plants, we know that they don't have any phase crossover at all. So that is, if there is no phase crossover, there is no question of instability induced by you can take a simple proportional controller. Now let us try to bring some time delay for the same plant. So I'm trying to bring a same plant 100 by s plus 10. I'm trying to bring a small time delay of 10 milliseconds. So if you have a small time delay of 10 milliseconds, let us see here the phase issue. You see here the phase, earlier for the same plant there was no phase crossover. Now for the same plant, the moment we are bringing this small time delay of 10 milliseconds, the phase crossover is appearing here. You can see the phase crossover appears, and it requires sufficient gain margin to stabilize. Now earlier there was no issue of stability. Now stability has become a concern as a result of the phase lag introduced by the non-union phase component in the form of delay term. Now you see here there is the basic idea typically one would use is to come up with a lead compensator that would improve the phase margin. So it is true. I mean, like when we add the lead compensator, so we can add a 0 and we can add a pole for its realization, and this 0 will significantly help us in improving the phase margin. So the idea is basically to add a 0 slightly to the right side of this gain crossover frequency to attain a sufficient phase lead. But whether this idea will practically work, the idea of adding a lead compensator has a limitation. The slope of the magnitude characteristics, if you add additional extra zeros to significantly improve the phase margin, it will not work, because what happens is that you add this idea of extending to additional number of zeros. What happens is that this magnitude after it starts increasing. It gets flat, and then as you add more number of zeros, this idea it becomes positive here, and then at high frequencies it increases. So as a result, what happens is that when the practical systems, there is always the issue of the noise. So whenever there is an external noise, the controller gain should be should be very low. But here this idea of adding a more number of zeros to improve the phase margin will not be will fail actually. Now so these non-union phase systems, if you see both this time delay and the 0 on the right hand side of the S plane, they basically modify the phase characteristics. They don't change the magnitude characteristics, and also this modification in phase characteristics is also not in terms of improving the control performance. Actually, they are actually in terms of degrading the control performance. Why? Because they are adding extra phase lag. If you see that minus omega t in the time delay term, they're actually creating extra phase lag, so causing the phase crossover if there was no phase crossover earlier. So this actually reduces significantly the stability margin of the overall system. So this is actually the problem of the non-moving phase system. So with this, we should have some sufficient idea what are the issues of this non-moving phase system. Now, if you still for the same plant, I have taken 100 by s plus 10 to understand. Again, I have increased the delay from 10 milliseconds to 2 seconds. If you see here, the magnitude has no issue, but you see here the phase has significantly dropped here. If you see, the phase lag becomes much larger, and the phase plot quickly reduces the negative values. You see here, it quickly reduces the negative values at somewhere nearly 2 radians per second itself. So the phase crossover frequency is much less than the gain crossover frequency. So these kind of plants, if you want to design a controller, you have to pull the gain crossover frequency to be less than the phase crossover frequency. Only then we will be able to attain positive gain, positive phase margin, so that we get the stability. So which means the moment I increase the time delay to 2 seconds, the phase has decreased significantly. As a result, I have to reduce its gain crossover frequency or its bandwidth. You see, to less than 2 radians per second, which means the amount of the signals for reference tracking or for the disturbance reduction is very much limited actually. So that's the problem of this non-minimum phase plants. So for the same plant, again 100 by s plus 10 e power minus 2s to stabilize, I have used the integral idea. So by using this integral compensator, I have used the idea. So what I have done is, you see here, the red color is the plant, open loop plant, and this plant with the integral action is the blue. You see here, I have significantly reduced less than 2 radians per second, so that the gain crossover frequency is in the process of stabilization. The gain crossover frequency has to be much significantly less than the gain crossover frequency of the plant. So that's what I mean, like the amount of the kind of reference signals, the kind of disturbance signals that we want to reject and we want to track are very much limited actually. So this is the takeaway point that we need to understand clearly from the non-moving phase system that exhibits either time delay or a 0 on the right hand side of the S plane. So we can't get sufficient gain to offset frequency in the process of stabilization. Forget about the improving the performance. First we need to stabilize this kind of plants in the closed loop. Now you see here for the same I have looked at the closed loop step response. Even though the open loop plant can stabilize, can settle around 100 milliseconds, but a time delay of 2 seconds is making the plant, you see here, it is taking 25 seconds. So the plant can settle in 100 milliseconds, but a time delay of 2 seconds is making the plant to settle in 25 seconds. So it is very sluggish response. This is what we can expect from the non-moving phase systems. Always, like, they are very sluggish, they exhibit sluggish response. So what happens is that these feedback controllers, which are typically employed to track these reference signals and reject these disturbances with frequencies that are greater than WGC of plant control, you can't employ a simple feedback controller. So we'll see how this internal model control framework will help us in improving the in giving us the stability as well as in improving the the transient performance. I mean, like, to overcome this sluggish response. So again, qualitatively, I will not take much details of RSP0. It is qualitatively similar to the time delay. So again, here also one can look at the frequency response. Again, if you see here, the magnitude does not create any issue, but the phase is the culprit. I mean, like, it is going to significantly reduce the phase margin. So if you see here, again, it is also going to create a phase lag. So as a result, it is going to reduce, I mean, like, it is going to significantly reduce the stability margins. Now, how to overcome this using model-based control is the model-based robust control in particularly is the overall idea of this particular talk. Now let us look at the definition of model-based control. So the definition of model-based control says that we need to explicitly use the plant model in deriving the control law. So in particularly, using the inverse of the plant model is the basic idea in the model-based control, and how this inverse of the plant model will help us in improving the closed performance. So this is the basic simple idea. If we know I'm giving the control input D, and to achieve the output V, I'm using the plant model gain. So if I can use the inverse of this plant model gain, and is it possible for me to tailor what is the amount of input that I should supply to achieve the desired set point? So this is the idea, and this is the idea which is used actually in model-based control or model-based even predictive controllers. But this model-based predictive, these model-based controllers, they are actually operated in open loop control configuration. If you see here, this is a plant PM. It is having an input D, so it is actually D of S. So so please understand that it is D of S. I'm using as a D. So if I use D, and if I can get V of S, and if I can choose the controller to be the inverse of the plant model, you see here, I can achieve the instantaneous control. So it is very simple. I mean, like, I'm trying to simply inverting the plant model to achieve the instantaneous control. I mean, like, I'm able to track the set point instantaneously. But is it possible in practice? And how to use this model-based control is is it possible to to get the instantaneous control? But you see here, it's not possible to achieve this instantaneous control. There are few limitations. So let us look at the few limitations. So to get the instantaneous control, we should have a perfect model. So in the sense, we should have this inverse to be exactly canceling the actual plan. So constructing I mean, like, the perfect model is actually not possible in practice. So there is so as a result, what happens, this plant model mismatch will arise. So there is a difference between the actual plant and the model that we come up. So as a this plant model mismatch does not allow to reach the desired set point. So the basic idea is to take the the feedback of the plant model mismatch. Instead, the typical feedback configurations takes only the output as a the output measurement as a feedback. But let us try to understand clearly how this motivates to go to internal model control framework. Here, if we can take this plant model mismatch as the feedback in the open loop control to achieve the instantaneous control, will help us actually, because we want to achieve the instantaneous control. So how to achieve the instantaneous control is, if you can take this plant model mismatch as the feedback, we will see how it will help us. Now this open loop control, again, it is not possible if the model there is an issue of invertibility. So whenever there is a time delay and a 0 on the right hand side of the S plane in the plant, so it is not possible to invert the plant model. See, to achieve the instantaneous control, we need to invert this plant model. First issue is we will not be able to get the perfect model. Second issue is, the inversion. So the plant inversion, it is not always, possible, particularly when we are trying to deal with the non-minimum phase plants. So this idea also, it will not work, because if you see, if I want to compute the control input at the present instant, I need to have the measurement at the future instant, and the output at the future instant, and the derivative of the output at the future instant. So it is practically, it is not possible. So this idea of inversion for non-minimum phase plants has to be done carefully. Now the third issue is invertible plant may not be a proper transfer function. So if you have such a kind of transfer functions, if you use the inverse of the plant model, so practically it is not possible, because we know that, we should have more number of poles than the, at least more number of poles than the more number of zeros for its physical realizability. So this is also an issue. So how to overcome is by cascading the filter. So we'll just see how to do this idea. Now again, the issue with the open loop control is they don't have the ability to reject the disturbances. But what is the advantage of the open loop control is the instantaneous control. So we'll have the output to track very instantaneously, but there are these limitations. So how to overcome these limitations is through the internal model control framework. We will see how does this IMC is different from the the feedback configuration. So this is the basic structure of internal model control, and in particularly this is 1 degrees of freedom. So we will see what is the meaning of 1 degrees of freedom and 2 degrees of freedom in the coming slides. But let us try to understand how this this IMC controller or this IMC structure particularly is going to help us in improving the performance and the stability. So this you see here, let us try to understand the working of this IMC structure. Try to assume, consider that there is no external disturbances for the time being. So there are no external disturbances, and assume that the plant and the model are same. There is no mismatch. So when there is no mismatch between the plant and the model, you see here the signal that will be coming here is 0. So there is no feedback actually. And if I can choose my controller to be the inverse of the plant model, so what happens is that I'll still be able to achieve the instantaneous control. So V of S, by VSP is equal to 1. So I'll still be able to achieve the instantaneous control. Now, if you see here, now assume that the external disturbances are available. Like the external disturbances are happening. Now, if you see here, these external disturbances are happening. Again, consider that there is no plant model mismatch. Under the assumption of no plant model mismatch, at this point, we'll be able to get the effect of the disturbance estimate. So this point particularly gives the the plant model mismatch, and this particular point gives the disturbance estimate. Now using these two things, we can design the controller. So we can still design the controller using this disturbance estimate and to reject this disturbance, and still we can design this controller by considering this plant model mismatch to overcome this uncertainty, and still we'll be able to get the instantaneous control. Now, these are the advantages. Like we need to understand, under the assumption of no plant model mismatch, but practically there is always a plant model mismatch, and how to, overcome this plant model mismatch. We'll see, like this robustness, how it is going to, guarantee the robustness. Now, if you see here, the important thing is we need to look at the input and the output relation. So this is 1 degrees of freedom IMC, so it is little easy to understand. If you see here, this the input and the output relationship. So if you see here, there is one output, so V of S, and there is the input is a set point, and this is the disturbance. So this particular portion is, you see here, it is different from conventional feedback control structure. So PC by 1, typically if you see fundamental, the feedback control structure, it is PC by 1 plus PC. But here in the denominator, you see here, there is explicit account of plant model mismatch. And here also for the disturbance, there is explicit account of plant model mismatch. So this particular structure explicitly gives the plant model mismatch when compared to the feedback control architecture. And there are 3 basic properties of this IMC structure. Dual stability. So if the open loop plant is stable, the closed loop stability is guaranteed, because the control is typically chosen as the inverse of the plant model. Because so that's what, if we choose the plant to be stable, and if the controller is stable, the overall closed loop stability is guaranteed. And it does not have any steady state offset. We'll see why it does not have the steady state offset. Is by simply choosing the controller to be the inverse of the plant model, it is giving you the inherent integral action. Unlike the feedback, the typical PID controller, it has the integral component which must be tuned, but here there is no requirement of tuning for the integral component. It is inherently inbuilt here. So these are the 3 the properties of this IMC structure. Now, if you see, this is what I have said. If you see the way the closed loop control schemes are shaped by using the sensitivity function and the complementary sensitivity function. So this is for the fundamental the basic feedback control structure, PC by 1 plus PC. This is we expect the complementary sensitive function to be equal to 1 over a range of frequency, and in the same range of frequency we expect the the sensitive function to be much less than 1, so that we can get disturbance reduction and the robustness. But here, if you see here in conventional feedback control architecture, we do not there is no straightforward relationship between the controller tuning and the sensitive function. And similarly for feedback for the complementary sensitive function. So this is what the basic problem in the feedback control architecture. So we cannot shape both S and T simultaneously, but whereas in IMC we can shape independent, simultaneously and independently. And how this set point filter will help us is the set point filter. Here we are going to add a set point filter. So the basic advantage or the basic necessity of the set point filter is it deals with the plant model mismatch and unmeasured disturbances, and the tuning is very straightforward to attain the robustness and good disturbance reduction. These are the two advantages of having the set point filter. So you can have an explicit handle over the speed of this set point tracking response and for this disturbance reduction. And in IMC, tuning is much transparent. Actually, the meaning of transparency is if I can, we can do online tuning much straightforward. Unlike in the feedback control, for what values of the controller parameters, what could be the desired response. So it is not actually not transparent. But whereas in IMC structure, it is actually transparent. So I can simply tune a simple one tuning parameter to attain desired closed loop desired transient response in terms of overshoot and settling time. Now, to understand, I have taken again a few examples for a 1 degrees of freedom IMC. So I have chosen both the plant, and there is no plant model mismatch. That's what meaning of P of S is equal to PM of S. There is no plant model mismatch. Again, I have chosen the disturbance dynamics also similar. And I choose the controller to be the inverse of the plant model. And here a value of lambda is equal to 0.2 is chosen. So I have chosen in such a way that this noise amplification value of 20. So I have calculated this control effort and the output. So control effort is this one. The meaning of control effort is what is the plant input. Now, if you see with these values, this is what I'm able to achieve. I mean to say the regulatory response. So I'm basically giving a step input as a disturbance. You see here, I'm basically giving a step input in the disturbance, and this is what I'm able to get the response. I mean the transient response. You see here, this looks very sluggish actually. It is taking very long time to come back to the nominal point, to the nominal operating point. Now let us consider that. So I will not go into this detail of 2 degrees of freedom. See, consider that there is a 2 degrees of freedom IMC. Now you see here, I'm trying to compare 1 degrees of freedom IMC versus a 2 degrees of freedom IMC. So you see here, this red color is taking very long time. Now, whereas this blue color is the 2 degrees of freedom IMC, you see here, there is a step disturbance is applied and it is taking very short time. And actually it is coming back to the nominal operating point very quickly compared to a 1 degrees of freedom control. But you see here, it is taking a more control input. The blue, it is taking more control input compared to a 1 degrees of freedom IMC. So what we need to understand is that there is a trade-off. So you want to recover back to the nominal operating point quickly, you need to apply more input, and it is still possible to get through significant improvement in performance through 2 degrees of freedom IMC. So let us see what is a 2 degrees of freedom IMC compared to in what way it is different from 1 degrees of freedom IMC. You see here in the 1 degrees of freedom IMC, there is no disturbance filter. You see here, there is no disturbance filter. There was only one controller cascaded with a filter that should take care of both the set point and the disturbance rejection. Whereas here we have two controllers actually. I mean like CS into FR of S and F eta of S. These are the two controllers. In particular, we can say two filters, FR of S, that is the set point filter, and F eta of S is the disturbance rejection filter. So using these two filters, if I can tune these two filters, I can able to achieve effective disturbance rejection by using F eta, and I can achieve effective set point tracking by using FR of S. So this is the meaning of 2 degrees of freedom IMC. Means we have two explicit filters. So as usual, I mean like it does not change the properties of the IMC. That is, if the open loop plant is stable and the control is stable, then the closed loop stability is guaranteed actually. So how actually the meaning of how this 2 degrees of freedom IMC works, if you see here, it does not change fundamentally from 1 degrees of freedom IMC, but you're explicitly getting this f theta of s into this complementary sensitive function, and this is sensitive function. So if you consider this under the assumption of no plant model mismatch, now this will be the nominal sensitivity function, and this part will be the nominal complementary sensitive function. So shaping of nominal sensitive function will help us in enhancing the disturbance rejection. Let us try to see how it is going to enhance the disturbance rejection. And shaping the complementary sensitive function, that is PCFR, is going to enhance significantly the servo response. So how it is going to significantly enhance the disturbance rejection and the servo response, let us try to understand here. So under the assumption of no plant model mismatch, the denominator is equal to 1 here, and here also the denominator is equal to 1. And we are considering this, it is a model-based control. So the idea here is to use the controller to be the inverse of the plant model. So I'm trying to choose C equal to inverse of the plant model. Under the assumption of no plant model mismatch, I can do this. So this C and P will get away, and I have only FR. So by choosing FR, that the tuning parameter of FR, I can get close to the instantaneous control. So that's how I'm able to enhance the tracking or the servo response. Now you see here, again here denominator is equal to 1. If I know the disturbance plant dynamics here, I can cancel the disturbance plant dynamics with the roots of this numerator. Actually, this is the basic idea of enhancing the disturbance rejection here. So if I know the roots of this numerator, and if I can make these roots to have the poles of P eta of S, I can effectively cancel these, and I can make V naught of S by eta of S to be very much a very smaller value. So that's the idea here. So and moreover I can shape this sensitive function and complementary sensitive function independently. So shaping FR of S does not change change the sensitive function, and tuning F eta of S does not change the complementary sensitive function. So I can shape independently, which is not possible again in feedback control architecture, whereas it is possible here in IMC structure. And as usual, this property, three properties: dual stability, perfect control, and zero steady state offset. So the meaning of zero steady state offset is inherent integral action. You see here, the integral action is inherent, unlike if you take a simple PID controller. So Kp plus Ki by S. So there is a Ki by S. So there is an additional tuning parameter for integral action. So the integral action, the effectiveness of the integral action depends upon the value of Ki in a typical PID controller. But whereas here it is inherent, actually the integral action is inherently built, and we don't require any additional tuning parameters. So that's another advantage of using IMC structure. So we can get effective disturbance rejection, we can get an effective improvement in the servo response, and we don't require an additional tuning parameter for the integral action. And moreover, the tuning of FR and F theta are very straightforward, unlike in the feedback control architecture. Now there are three design simple steps in particularly when we are trying to deal with the non-minimum phase plants, like time delay or zero on the right hand side of the S plane. So the three steps is, so the meaning of design is, the meaning of design includes designing of controller, design of set point filter, design of the disturbance filter. So these are the three design the components that we need to do. So before going to the design, whenever we encounter a non-minimum phase plant, first step is to decouple the minimum phase part and the non-minimum phase part. I mean, like this plus stands for the non-minimum phase component, and minus stands for the minimum phase component. So first step is to you need to factorize, or you need to decouple this minimum phase component and the non-minimum phase component. And once we do this, we can design controller. So the controller, again, as usual, the way we need to use in the model-based control, choose the invertible portion of the plant model. So we are trying to choose the invertible portion of the plant model, because if you choose this non-invertible portion, the controller becomes unrealizable. And so that's why we avoid this one. I mean, choosing this non-minimum phase component, the control realization. So we choose only the portion which is invertible, that is PM minus. So moreover, we have seen that inverting the plant model gives improper transfer function. So to make it realizable, we cascade with the filter FRFS, so which is nothing but a set point filter. Here we have two tunings, how to choose the value of n and how to choose the value of lambda r. So the value of n is chosen in such a way that C of s into f r of s is basically realizable, and lambda r of s is a tunable filter time constant, which is nothing but a closed loop time constant. And we will see how to choose lambda r by taking a simple practical example. And there are two design approaches for effective disturbance reduction. So the approach one is designing through IMC IAE. IAE stands for integral absolute error design. So in this minimizing integral absolute error design, we need to factorize this planned model in this fashion. Like we need to take only the RSP0 outside, and whereas minimizing this integral square error, we need to have additionally the pole is similar to the RSP0. So these are the two ways of factorizing the planned model: one through to minimize integral absolute error, one to minimize integral square error. Now once we have once we have done this factorizing the planned model and based on the IAE factorization and IAC factorization, the third component involves the design of the disturbance filter. So the disturbance filter is chosen in this fashion f eta of s, and we need to design f eta in such a way that we get the effective disturbance reduction. Like we need to cancel the roots of this with the the poles of the disturbance transfer function. Here we need to find the values of lambda I and so on, and here m decides m is the nothing but the number of poles in the disturbance transfer function f p eta of s, and lambda d is the filter time constant similar to lambda r, but however lambda d decides the regulatory behavior and lambda r decides the servo behavior. So lambda r decides the servo behavior in the sense the tracking behavior, and lambda d decides the disturbance reduction the behavior. So how to get the values of alpha 1, alpha 2 and so on, so and lambda r and lambda d. So we need to have these values, and this can be attained by solving this equation 1 minus this is basically nothing but the sensitivity function. We are trying to solve this sensitivity function for all the poles of the disturbance transfer function p eta of s. So this is the basic idea here and the design of f eta. Now, if you see this non-phase power electronic converters, I am taking the basic power electronic converter, which is a simple boost converter. However, there are many other high-gain converters which comes under the class of non-phase power electronic converter. So these power electronic converters are used in day-to-day life, renewable energy, and mobile applications, electric vehicles or fuel cell electric vehicles, hybrid electric vehicles, and but these power electronic converters, particularly these high-gain converters, this is boost converter or a high gain converter, but this is a conventional high gain converter where the gain is limited limited to 3, I guess. I mean, like limited to 3 between the output voltage and the input voltage. I mean, the 3 in the sense, if the input voltage is let's say 10 volts, you can get a maximum output voltage of 30 volts. That's the meaning of gain equal to 3. And there are many high gain converters, but however all those high gain converters typically comes under the class of non-minimum phase system. We see why this is called a non-minimum phase system. Let us try to understand in a simple manner. You see here, here this is a MOSFET switch. This is given through a gate drive pulse, which is on and off. So whenever it is on and whenever it is off, we basically get two linear circuits. You see here, this is a linear circuit, this is a linear circuit. This is a linear circuit when this MOSFET switch is in on condition, and this is a linear circuit when the MOSFET switch is in off condition. You see here, whenever this switch is in on condition, the inductor is going to charge. However, this output voltage, this capacitor is getting discharged through this output resistor to the load. So which means the inductor is charging in this fashion. You can see here, I'm just trying to say this is how the inductor charges, whereas in the same duration, the output voltage is discharging actually, because we are having a load is expecting the output voltage. However, there is no connection between the input and the output sides. You see here, the energy from the input side is not being transferred to the load side in the same cycle. So we need to wait basically till we come to the off cycle. So in the on cycle, inductor charges, and in the off cycle, whatever the energy that is stored, the inductor discharges with a negative slope, and then the capacitor builds its energy. That's how we sorry. So that's how this is actually a two-stage process. That's the reason why this is coming under non-minimum phase dynamics. In the same switching cycle, this inductor is charging and inductor is discharging in the another cycle. Now that is one issue that comes under the non-minimum phase dynamics. And the second issue is, if you see here, this high gain converters, as you increase the duty ratio is nothing but the plant input here. As you increase the duty ratio, after a certain after certain plant input, you see here it is increasing its gain. So that's why I have said that it is a high gain converter. But after duty ratio of 0.9 somewhere, the gain is getting significantly dropped. I mean, it is no more a high gain converter, or it is no more a boost converter. It suddenly drops. So one has to take sufficient care to have its duty ratio limits. So what is the duty ratio upper limit and what is the duty ratio lower limit while designing the converter? So here when I design, so the gain is somewhere around this is the the simulated model. So the simulated model is somewhere up to 0.8 is linear. After the increase of gain is pretty much slow, and suddenly it drops. And if you see, I have done for the practical converter. The practical converter, after gain of 0.75 or 0.7 somewhere, the gain suddenly drops again. So that's the, if you see here, this is the culprit, this RL by 1 minus D whole square into R. This is the reason why this gain is suddenly dropping. Under the ideal case, RL equal to 0. So under the ideal case, you get infinite gain. Under the practical case, the gain is limited by RL. RL is nothing but the inductor ESR. Now its transition behavior, if you see, this is the control pulse. If you see the transition behavior, why it is exhibiting the inverse response or non-minimum phase dynamics, you see here, D is the plant input, that is the duty ratio is a plant input. V0 output voltage is the measured output. So you see here, for a positive increase in the inductor current, or for a positive increase in the duty ratio, the inductor current is increasing, whereas the output voltage, you see here, it suddenly decreases. Actually, initially it decreases and then it increases. So you see here, even though you're increasing the duty ratio, the inductor current is increasing, but the output voltage is initially going down, because the input, you see here, the load is actually initially disconnected. So that's why when the load is disconnected, this capacitor is getting discharged initially. So that's the reason why it is going in the negative direction, even though you're applying the positive input. The capacitor is basically getting discharged. So, and then it takes some sufficient time for the inductor to build, and then make the capacitor to follow as per the input. So this is we call it as an inverse response, and it is coming because of the non-minimum phase dynamics that is inherently incorporated or inherently there in this boosted DC converters or the high gain converters. So since it is having an inductor and a capacitor, it is basically a second order plant. And the issue with this RSP0, as we have already seen, it is quite similar to the time delay. But if you look at the frequency response, the RSP0 basically has with respect to magnitude response, it basically behaves like a LHP0, and with respect to phase response, it behaves like a RHP pole. So this is a typical behavior of RHP0. So as you see here, as a result of RHP0, the amount of phase margin that is required is basically significantly low. So it does not drop, the phase margin does not drop at the point of RHP0. It starts decaying at least 1 decade before the RHP0. So if the RHP0 is here, you see here, if the RHP0 is somewhere here, it's the effect is seen 1 decade before. That's the reason why the amount of phase margin becomes very small or even negative. So that's a negative impact on the phase margin. So for more details, again, one can look at this Texas document. So how to get the sufficient phase margin? I mean, like how to get this stability and how to get improve its phase response using the internal model control. So typically the model is developed using the state space averaging method. The objective is to get this small signal model or the transfer function, and it involves 2 steps. So it basically converts a linear time varying plant into a non-linear time invariant plant, and one should look at the linearization to get a linear time invariant model at around the operating point. And here for this kind of power electron DC converters, the control input is the duty ratio and the controlled variable is the output voltage, and these external disturbances are the variations in the input voltage and the load current. And in particular, this kind of converters has an additional challenge of RHP0. So you have basically these control objectives. The control objectives are basically the regulatory control and the servo control. So regulatory control is you're expected to have a constant output voltage in the presence of external disturbances, that is variations in input voltage and variations in the load current. And the second objective is the servo control. So we're expected to have the desired set point tracking, which is higher than the input voltage. And in the process of regulatory control and servo control, there are practical control limitations. The practical limitations are the amount of the duty ratio is basically constrained actually. So even though theoretically we say particularly for this kind of high gain converters, the duty ratio is between 0 to 1, but you have already seen from this the simulated value, it is actually not from 0 to 1. So somewhere this is for the simulation model, I have this somewhere value somewhere around 0.9. So after beyond 0.9, it is no more a boost or the high gain converter because the gain is getting reduced. So for a practical model, it was somewhere around 0.7. So that's the meaning of practical challenge, that is the duty ratio is actually always constrained. And in addition to constraint, it is actually reduced compared to even again what we see in the theory, the theoretical derivation, because the gain is being limited by the inductor ESR. You see here, this is the reason why the gain V0 by Vi is getting limited by this factor actually. So in addition, what actually we are expected, because when we are trying to deal with the practical systems, we are expected to have we're expected to use a reduced number of sensors to improve the overall reliability of a closed loop system. So with this regulatory control, servo control, and keeping in mind that the duty ratio is practically constrained, and we were expected to use a minimum number of sensors to improve the reliability. So we'll go ahead with the control design. So I have used both compact Rio FPGA platform and Opal RT platform, to get the experimental results. And you see here this boost up DC converter when we design in continuous conduction mode. So there are two conduction modes of these converters. One is continuous conduction mode, the other is the discontinuous conduction mode. So this RSP0 comes across in the continuous conduction mode. And moreover, these converters are expected to operate in the continuous conduction mode because the efficiency is higher, the current ripple, voltage ripple is much smaller in the continuous conduction mode compared to the discontinuous conduction mode. And we can see here the transfer function is having an RSP0, and there are two disturbance models. One is the input voltage variation, the other is the output current variation. We will see how we can use this disturbance model as well in the the design of internal model controller. So, but typically, let us look at the conventional control schemes that are employed basically for this parallel converters are basically current mode control. So this is the structure of the current mode control. This current mode control employs two controllers, one outer loop and the inner loop. So this outer loop is the voltage controller and the inner loop is the current loop controller. However, this inner loop current control requires the sensing of the inductor current. In addition to sensing of this inductor current, this current mode control scheme exhibits instability, inherent instability, irrespective of any converter. So this is how I have represented a DC-DC converter. Irrespective of any DC-DC converter, this current mode control, typically which is employed, in particular the peak current mode control, goes into instability for a duty ratio greater than 0.5. That means the input, the plant input, whenever the plant input goes to greater than 0.5, it goes unstable. And it requires sufficient slope compensation techniques to stabilize, which are again not transparent. And moreover, this by using this additional current sensor, which is actually sensitive to noise. See, I'm trying to speak in terms of the practical system. So you need to encounter into noise as well. So this current sensor is basically sensitive to noise. Moreover, so even though they are conventionally used in the industry, but they are actually not attractive for the industry applications. So as a result, we have on the other hand, there is a voltage mode control, which is a single loop control. So you see here, this is a single loop control, but this single loop control has an advantages, but it has some some limitations. The advantages are it does not have a limit on the duty ratio, unlike the current mode control. Duty ratio is restricted to 0.5. So here there is no such duty ratio limit, and there is no requirement of additional current sensor for measuring the inductor current because it is a single loop control. So it is a better solution. But what is the limitation is, so whenever you have the plant which is having an RSP0, the single loop control exhibits a sluggish dynamic response. So even we have seen initially the idea of lead compensator and the idea of the integral controller, the plant is giving a very slow response. So this is the same thing. This single loop controllers for RSP0 gives sluggish response. So to improve its performance, typically it uses feed forward control. You see here, it is using a feed forward control. But so our objective is to have to reduce the number of sensors. So we do not want to use this feed forward control, but again with the use of single loop control, that is under what we call it as a voltage mode control, is it possible for us to improve its performance without using the feed forward control? So it is still possible using the internal model control structure, and still it is possible using the PID control, but we need to employ the kind of tuning techniques. So in this work, in this talk, I will use the IMC. You see here, typically this is sliding mode control and this hybrid control algorithm, which are available in literature, which are actually robust control, which, and moreover, these control schemes, this is sliding mode control, even though they are, they give a good performance, but they have its own issues when we go for the practical implementation. The issue is that this implementation of sliding mode control requires several sensors. It requires sensing of inductor current, it requires sensing of capacitor current, it requires sensing of input voltage. So failure of any one sensor actually does not guarantee the performance and does not guarantee the closed loop stability. So that's the problem with this sliding mode control and this hybrid control algorithms. So there are majority of control algorithms that are available for power converters, but they, when it comes to use of a single sensor, all these control schemes will does not fit actually, because the failure of even a single sensor actually completely the output goes completely unstable actually. So we need to have a closed loop control scheme which is robust and which employs single sensor. So such is a scheme, and it should have the ability to encounter RHP 0. So that is the kind of structure which is actually IMC. It, because it has all these advantages actually. So it can so this is actually the problem statement we can formulate in this way. So IMC controller with anti-reset wind-up compensator. So we will see what is the meaning of anti-reset wind-up compensator in the coming few slides. For a non-minimum phase DC-DC boost converter, using only sensed output voltage as a feedback. So I want to sense only output voltage as a feedback in improving its closed loop performance. So in improving closed loop performance without requiring additional sensors for input voltage, load current, and inductor current, where typically this sliding mode control, hybrid control, many other all majority of the control schemes employ so many sensors actually. And moreover, this closed loop improvement of this closed loop responses has to be investigated under large set point changes. But whereas typically in the literature, majority of the works has not been investigated for large set point change. So that's the reason why we had taken into this work. Even sliding mode control, almost majority, I mean 90 or 95% of the works have not touched this issue of large set point change or the large variations in the disturbances. And so that's how we come up with the research contributions employing IMC, and we found that there are even limitations with IMC, and how to overcome these limitations with IMC in the form of additional degree of freedom, which is called the anti-reset wind-up compensator. So this is so I have which explained IMC can be designed for minimizing integral absolute error, integral square error. So these are the expected or the resulted controllers, planned set point filters, and the disturbance filters. So we have started with the simulations, and then we have conducted the experiments on a practical booster disease converter. So let me explain some of the results. So how the reason why we encountered this simulation is we want to look at the robustness under the under the plant model mismatch. You see here the thin lines. You see here there are 3 thin lines and there are 3 thick lines. So this first category is we are given a sudden disturbance. So the input voltage is 10 volts is the nominal. We have given a 30% variation. So 10 volts to 7 volts is the sudden step disturbance we are given. So under this step disturbance, this you see here these thin lines. These are the linear simulations. The linear simulations in the sense there is no plant model mismatch. So when there is no plant model mismatch, you see here integral IMC controller with IAE factorization is having an upper hand over the other 2 controllers. That is ISC factorization and the PID controller, because this conventional PID controller does not account the RHP 0. So there are different ways of designing PID controller. So the conventional PID controller does not take into account of RHP 0. That's why its response is very sluggish. And you see here again we have encountered in the nonlinear simulation, that is we have looked at the plant model mismatch. We brought the plant model mismatch into practice. The plant was actually deployed using the Simulink model. So the moment we brought this the plant model mismatch, you see here there is a difference between this peaks actually. So, but even though you see here, even though there is a difference in the plant model mismatch, still this IMC controller with IA factorization is having an upper hand over the other two controllers. So similarly, on the other hand, we have given other 30% variation, that is 10 volts to 13 volts. So this is another disturbance we have given. Even here also we can see that IMC controller with IA factorization in both the linear simulation and the nonlinear simulation. So the meaning of linear simulation is there is no plant model mismatch, and the meaning of nonlinear simulation, there is explicit plant model mismatch. So in both cases, we have seen that IA factorization is having an upper hand over the IC factorization. So let us look at the tracking response. Even the tracking response, there's a linear simulation and there is a nonlinear simulation. You see here PID control is taking very long time because this conventional PID does not take account of RSP0. That's the issue with the typical PID controllers. And you see here with IA factorization, it is having a smooth tracking response, and with IC factorization, it is having a slightly overshoot. So, but we should know why this IA factorization is giving an upper hand over the IC factorization under IMC controller itself. So that's a question that we should look at. So I will try to give the answer in the end. And again, we have done the experimental validation. So in experimental validation also, you can see here this red color is having an upper hand for the same disturbance. We have given 10 volts to 7 volts, so we have given 30% variation. So IMC control with IA factorization is having an upper hand over the other controllers, both in the nonlinear simulation and the experiments. And this is other category, and this is under the load variation. So even under the load variation, this IMC IA is having an upper hand. And you see here, this is close to DCM, that is the light load condition or the discontinuous conduction mode. Even under the discontinuous conduction mode, you see here this red color IMC controller is having an upper hand, but there is sufficient difference between the the simulations and the experiments in this particular case. So again, for the tracking case, you see here IMC control with IA factorization is having no overshoot compared to ISC factorization. However, PID controller does not have overshoot, but it is very sluggish. And you see here this PID controller. So you see here this the practical limit of duty ratio, that is the plant input, is restricted to 0.7 in the practical experimental validation. You see here IMC controller are using basically less energy. So this is a plant input. It is using less energy compared to the PID controller. The PID controller is basically hitting the saturation even for a small set point change from 15 volts to 19 volts. So similarly for the step down case, but so one can look at this performance indices in the paper. Now, what actually are the observations is, even though we have done IMC control both for IA factorization and IC factorization, IA factorization is having an upper hand, in all the case studies, like the disturbance reduction or the set point tracking, compared to PID as well. And what is the most important thing that what we have understood is that the performance of the controller tuned using the linear model, that is the transfer function, does not change significantly when used for both nonlinear simulations and the hardware experiments. I mean, we have not changed the tuning parameters. We have gone from linear simulation to nonlinear simulation and the nonlinear simulation to hardware experiment. So we have used the same value of the tuning parameters. So that's how we could say that, I mean, we are able to achieve, the plant model mismatch, there is a robustness. However, in addition, there is an interesting that we have observed is that this PID controller is hitting the saturation. I mean, it is going into saturation even for a small set point change for a brief amount of time, whereas IMC controller is not hitting the saturation and it is having a smooth transition. So, so let us look at what is the meaning of input saturation. So the other is the input saturation. So this input saturation occurs, or the duty ratio saturation occurs, whenever we encounter large set point changes or the large disturbances. And I have taken a case study of large set point changes. And what is the meaning of this anti-reset winder compensator, and what is its role in the input saturation? We will see now. So the problem statement is same, but we have looked at another objective, second objective, and we have contributed to a conference paper by developing the anti-reset winder compensation technique. So this is a problem statement. So I'm not changing the problem statement. And so this is IMC, how to use, deploy IMC for boost converter by integrating anti-reset winder compensator. But again, without using additional sensors, that is using only sensed output voltage as a feedback. So you see here, this is how practically we deploy this internal mode control for a boost converter. So we have already seen this. The controller is chosen as the inverse of the plant model because it gives the inherent integral action. Now, what happens is that whenever there are sudden disturbances or sudden large set point changes, what happens is this input gets saturated. That is, this D of S lies outside the limit of this saturation limits. Now, under that case, what happens is that this IMC controller C, it is unable to see the effect of D actually on the output. So controller does not know the effect of saturation on the output, and as a result, what happens is that the output voltage takes a long time, and it exhibits overshoots, undershoots, and sometimes it may even go unstable actually. Now, so what is the idea here is we need to halt this integral action. See, integral action is basically nothing but the accumulation. So we need to halt the integral action during the saturation, and how to halt this integral action during saturation is given by the anti-receipt wind-up compensator. And how to develop this anti-receipt wind-up compensator under the internal model control framework without disturbing the controller, without disturbing the set point filter, without disturbing the disturbance filter, is actually another critical actually problem that must be that has been addressed. So there are existing anti-receipt wind-up compensation techniques for IMC. So those existing anti-receipt wind-up compensation basically has a trade-off between the performance and stability, and requires the redesign of controllers whenever there is a saturation occurs. The meaning of redesign is we need to change the controller, we need to change the set point filter, we need to change the disturbance filter, and moreover there are lack of systematic tuning guidelines for the anti-receipt wind-up compensator. So these are the three major issues with the existing anti-receipt wind-up schemes under the IMC, and we have come up with an integrated mechanism. So this integrated mechanism gets makes this anti-receipt wind-up compensator gets activated only if there is a mismatch between the controller output and the plant input. So D stands for the controller input, and D stands for the plant input. And we have come up with a systematic design procedure for the anti-receipt wind-up compensator, and we have not sacrificed the performance during the normal operation. So we have not disturbed the earlier designed controller FR and F theta of S. And moreover, redesign of IMC is not required. So for the conventional anti-receipt wind-up compensation techniques under IMC, one can look at this International Journal of Control by Manfred Morari. So he is very renowned in robust process control, Manfred Morari. So one can look at this paper. So they have given the issues with the existing anti-receipt wind-up compensation. So couple of anti-receipt wind-up techniques they have addressed. So where they have given the trade-off between the performance and the stability, one has to sacrifice any one of them. However, in this proposed work, we don't need to sacrifice neither the performance nor the stability, nor we don't need to redesign the controllers. And in addition, we have developed the systematic tuning guidelines. So this is the anti-receipt wind-up mechanism that we have proposed to overcome this receipt wind-up problem. So whenever this D lies outside the limits of D star, so we better take the difference between these two, and then use the idea of the feedback control scheme. The idea of using the feedback control scheme is to employ a high gain controller. So here we are trying to employ a high gain anti-receipt wind-up compensator to reject or to nullify the differences between D and D star. We are treating this as the external disturbances for this anti-receipt wind-up mechanism, and we want to nullify this, and we are giving this information to the controller. So once we give this information to the controller, this reset wind-up mechanism helps us in desaturating this D actually. So, and it ensures the the set point, the large set point change V to follow V set point. As a result, we can get an improved performance in terms of reduced overshoot and settling, reduced settling time. Now so let us try to understand the dynamics of this loop, this particular loop under the saturation. So if you look at the dynamics, actually it resembles the it resembles the feedback control architecture. That's what I have said. We have used the idea of a high gain controller actually here. So if you see here, this is D, this is the controller output, this is the plant input. So the objective is we want to make D to be following D star actually. So you see here, D should follow D star, which means the controller is operating in the linear region. So that's what actually we want to achieve. So on how to achieve is by employing a high gain compensator. So we have not changed C, FR and F theta, and only we have brought A actually. A of S represents the anti-receipt wind-up compensator, and we have chosen a simple first order plant with a gain of K and tau as a time constant. So choosing K and tau judiciously will help us in improving the performance and will guarantee the stability. So what we have done is that we have used a very large value of K, and this large value of K, if you see here at low frequencies, this sensitivity function becomes much small actually. So this becomes much small and this becomes almost equal to 1. So when it becomes much small actually, so whatever the error is coming because of the large set point change, it is almost nullifying here. And when we choose a sufficient large value of k, what happens is that it becomes close to 1. So and we are able to achieve d almost equal to d star. So that's the meaning of operating in the linear region. So when we employ this idea of high gain large k, so this is what we are able to get. And if you see here, a value of high gain k, this becomes much small, and d is almost close to d star. The idea of high gain or high gain of anti-recessive wind-up compensator makes this d independent of the integral action of the controller. So this is actually the basic idea of developing the anti-recessive wind-up compensator. And moreover, you can see the stability is guaranteed by this denominator 1 plus c fr and a of s. So we have already designed c and we have already designed fr. Now we choose a, that is k and tau, in such a way that the roots of this characteristic equation determine the roots lies on the left hand side. So this determines the stability. And choosing k and tau, so we have also understood that k has to be very large value, but how large we need to know, and how to choose this tau. So this is the meaning of systematic tuning guidelines. So we have understood the basic idea of choosing a very large k. It is going to make the controller to be independent of the integral action of the controller. That is, this d becomes independent of this integral action. So that is the idea actually. So now we have tried for the values of k equal to 100 and k equal to 200. Now if you see from where these values of k equal to 100 and k equal to 200 has come, is from the plant actually. So that's why we call it as systematic guideline. So if you see here, the plant is having a gain of 22, steady state gain. So using this idea, what we have done is that we have chosen the value of k around 5 to 10 times. So the steady state gain of the plant is 22. So we have chosen around 5 and 10 times. And see here, for what value we should choose here, whether we should choose k equal to 100 or whether k equal to 200. For both the values, the anti-recessive wind-up compensation mechanism is going to work. But which value we should choose? So we have chosen a value of k equal to 200. It results in smaller magnitude of the sensitivity function. See, this is the sensitivity function for the internal loop, that is during the saturation, Si. So, and it also reduces the integral wind-up effect, but it is giving you larger crossover frequency. So when there is a larger crossover frequency, there is again an issue of noise. So it might encounter add some noise. So what we need to have is that at high gain, the roll of rate has to be much fast actually. You need to have a quick roll of gain at high frequency. So that's why we've got additional tuning parameter tau. So we have chosen k equal to 200. Now for tau also we have chosen tau equal to 0 milliseconds, tau equal to 10 milliseconds, and tau equal to 20 milliseconds. Now among tau equal to 20 milliseconds and tau equal to 10 milliseconds, actually tau equal to 10 milliseconds is going to help us in improving the closed loop response compared to tau equal to 20 milliseconds. Why? Because again we need to look at the sensitivity function of the inner loop. So for tau equal to 20 milliseconds, the you see here there's a peak coming here. For tau equal to 10 milliseconds, the peak is it is actually not amplified. The effect of anti-reset wind-up is not amplified with 10 milliseconds, but however, it is amplified in this portion, in this region. So that's why we can expect even before conducting experiments that k equal to 200 and k equal to 10 milliseconds is going to help us in significantly improving the response during the input saturation. And also it is going to give us the stability. So both stability and performance are achieved actually, which was not available in the literature. So this was the first work actually under the IMC framework. So we have done implementation by using the FPGA. So you see here this idea we have done in the simulation as well as in the experiments. So I will go to the experiments. So I have taken a case study. So this is the meaning of large set point change. So I have given a set point change from 15 to 28 volts. So this is a large set point change. So almost twice I had given. So you see here, whenever there is no anti-reset wind-up mechanism, this blue color is taking very long time to reach the desired set point, and also it is exhibiting overshoot. Whereas with the proposed anti-reset wind-up mechanism, there is no overshoot, and then it is reaching the desired set point with at a fast time, with a reduced settling time. Why it is happening? Because you see here, why? Because it is the plant input with the blue color is hitting the saturation and then staying actually. It is staying in the saturation region for a long time because there is no reset wind-up mechanism. whereas this red color, we're actually providing this anti-reset wind-up mechanism. It is coming out of the saturation. So the input is coming out of the saturation. As a result, we're actually getting an enhanced or the improvements in the output response, significant improvements. So similar, for step change in the from 15 to 11 is another case study. Here also it is the same thing. So the input is coming out of the saturation quickly. So as a result, there is an improvement in terms of the overshoot and the settling times. And here also you can see here there is a significant overshoot. There is no overshoot, and moreover the settling time has been reduced in this case. Proposed anti-reset wind-up mechanism. The case studies, this proposed work is showing promising results. So the promising results in terms of reducing the settling time and reducing the overshoots. So we have done this performance, the performance indices in terms of IAE error and then this settling time. So what actually we have achieved is, with the anti-reset wind-up mechanism for large set point changes, the input is desaturated quickly with the proposed technique when compared to without anti-reset wind-up mechanism. And this, proposed anti-reset wind-up mechanism, what we are able to achieve is we are able to achieve significant improvements in the transient response. That is, reduction in the overshoot and reduction in the settling time. And how we are able to achieve is by significantly, by making the plant input to come out of the saturation quickly. So let me conclude what actually we have achieved using this internal mode control from the beginning. So this IMC structure is able to provide the transparent tuning framework for the set point filter FR and for the disturbance filter F eta. And in particularly, it is able to help us dealing this non-minimum phase plant. That is, we're able to operate the non-minimum phase plant close to the non-minimum phase dynamics. So that's the meaning of that's the advantage of this IMC structure, which is not available with the other feedback structures. And we're able to see, we started with using a simple transfer function. The control design was started with a simple transfer function around an operating point, and we have verified for its robustness under the plant model mismatch in nonlinear simulation and in experiments. And we're able to see that it is able to achieve significant improvement performance in compared to other conventional PID and IAC factorization in particularly. So IMC controller with IAE factorization is ideally suited for non-minimum phase plants. So this is actually the conclusion. And however, this IMC controller with IAE factorization or even IAC factorization is having an the inherent limitation, that is the plant input saturation. And we have done for the IMC controller with IAE factorization the integration of anti-reset wind-up compensator. As a result, what happened is that we are able to achieve significant improvements in the performances, that is closed loop performances for large set point changes. And again, this does not require an additional sensor. So again, this is the the attractive feature of our work is a single sensor was sufficient to achieve all the goals actually, which was not available with any other control scheme like sliding mode controller or any other nonlinear control scheme in the literature. So let me stop here, and I would like to take a few questions.
Participants, you can unmute yourself for your questions. Otherwise, you can type your questions in the chat box.
If you have questions, you can type in the chat box. I think, let me see. Okay.
What are the challenges that you face while going for the real-time implementation of these controllers?
The real-time issue is see, if you see this, let me go back to the slide. The problem is actually Yeah, see, you see here, the real-time implementation actually requires, you need to have controller, you need to have filter FR, you need to have anti-event mechanism A, you need to have disturbance filter F eta, you need to have plant model. All these computations has to be done in a single cycle, switching cycle. So that's why we have done this implementation in the FPGA.
Okay. Any other question by participants?
Yeah, please feel free to ask questions. I'll be happy to address.
Because having the real-time experimentation is very difficult.
Yeah, actually, it faced lot of hurdles actually.
Yeah.
So otherwise, in case if you can't ask now, but at least you can feel free to write to me. I will be happy to answer. You can always approach me in these two mails. I'll be happy to address actually. If you want any information or if you want any other information that I can provide, I will be happy to provide actually.
Yes, sure. We can share this with the participants and we can get that.
Yeah, yeah.
So thank you very much, sir, for sparing
Yeah.
time.
Yeah,
Thank you very much
thank
for
you.
accepting
Thank
the
you so much.
invitation and delivering the talk. It was really a wonderful talk with real-time experimentation.
Yeah, thank you so much, and I'm glad that I got the invitation from you. So I'll be happy to continue, or any other form you want me to help or collaboration, or I'll be very happy to do it.
Yes, yes, sure, sir. And if you,
Yeah.
if you happen to pass through Nasik or nearby Nasik, please visit our institution.
Yeah, sure, definitely. I'll be happy to visit your institute.
Yeah.
Yeah.
Mary?
So we have concluded, you are concluding the first days, FTP first day. So I am sincerely thankful to Dr. Tarakanath Kobaku for delivering such an engaging session. Your valuable presentation and very clear explanations have greatly enhanced our understanding of the topic. We truly appreciate your time and expertise you shared with all the participants. Thank you for your contribution, and we are further expecting your support in our future too. So with this, we are concluding today's session. Tomorrow, we will be having two sessions as per the schedule. Thank you so much for all the participants. We will meet in tomorrow's session.
Yes, thank you. Thank you, sir.
Thank you. Yeah,
Thank you,
you.
sir.